The algebraic representation of vectors. When placed on the coordinate plane, a vector has a vertical and horizontal change from tail to tip. Therefore, a vector can be written in a component form, which would be the horizontal change and the vertical change. Okay, now what you're going to notice here as far as notation would be these symbols that look a little bit like parentheses but aren't. They actually have a little bit of a point on them, which you're going to notice down here next to V and U as well. Okay, so when you see that, they look like parentheses, but they got the little points on them. What that will actually indicate is you are not looking at a coordinate, but you're looking at the components to a vector. Vector V has two components, a 2 and a -3. The 2 is going to be a component in the horizontal direction, and it's going to indicate, because it's a +2, that it will be moving to the right. The -3 is going to be a component in the vertical direction. Because it is negative, it's going to indicate that it is moving in a negative or down direction to that. Okay, so a picture of vector V. I do have a grid here, but notice that I don't have an origin or any axes here. Okay, recall that a vector is going to be defined by a direction and a magnitude. It is not defined by a location. So literally anywhere on the plane, I could sketch a picture of this vector. Okay, let's, because it has a down component, let's say that it starts here. The 2 tells us that the vector is going to be going 2 units to the right. The -3 is going to tell us that the vector is going down 3 units, okay? So I'll go over 2, go down 3, and that would be the end of vector V. Okay, so this is what it looks like. That is vector V. Okay, and that just gives a different description of the vector. So instead of having the true length of this, like the magnitude, and then a direction that would be based off of an angle measurement, you can actually just describe it with a horizontal and vertical component. Sort of like slope, except that you're actually using endpoints. Okay, vector U is a 0, 5. The 0 indicates that this vector does not move left or right at all. The 5 indicates that this vector is moving up 5 units. 1, 2, 3, 4, 5. All right, so that's going to take up all my boxes here. Okay, so this could be vector U, which would be heading in that direction because you've got the +5. In example 2, you're going to notice that both A and B have parentheses. That's going to indicate that these are actually coordinates. We're going to plot these coordinates and then create a vector, which would be vector AB. Okay, so it's going to start at A and then go to B. We're going to figure out the component form for that, and we're also going to calculate the magnitude of that vector. All right, so to do that, we are going to have a coordinate system. As far as the points, because that goes as far out as 9 units and then goes down 1 unit, what I think I can do is just set this up. You might not be able to see that very well, but I'm going to set that up as my origin right here. I'm going to put a little dot, just make sure it shows up. Okay, so that'll be my origin. Point A is going to be at 4, 2. Okay, so that's A. And B is going to be at 9, -1. So that's 4. We've got 5, 6, 7, 8, 9. And we'll be down 1 at B. Okay, so this is our vector, which is based off of a couple of points that are in the coordinate system. Okay, the component form for this, okay, we're going to use this notation. The component form from A to B horizontally would be 5 units. You actually got to go from 4 to 9. Vertical will be moving in a down direction 3 units. So put -3. Okay, and those would be the components for vector AB. As far as the magnitude, because we have the components here, because we have those, you can basically do some Pythagorean theorem. All right, here are your components. You've got a 5, you've also got a 3. That would be a -3, but when you do Pythagorean theorem, it does become positive, so we don't really need to worry about that. All right, so we're going to take 5 squared plus, we're going to take 5 squared plus 3 squared, which is going to be 25 plus 9, which equals 34, and then the magnitude, we can describe that as the square root of 34. Okay, so AB, vector AB's magnitude is going to be equal to the square root of 34. That, of course, was our component form. One of the benefits of using component form is that it can make adding or subtracting vectors much easier. It really could. If you had two vectors, v and u, and let's say that v is a, b, those are the components of it, that means horizontal a, vertical b, whether they be positive or negative. If you've got those components and vector u has these components, c, d, and you wanted to add them together, what you can literally do is add the horizontal components together. You can take the a and the c and go ahead and add that. You can take b and d, go ahead and add that, and that'll create a new vector that would represent the resultant vector to it. Real simple process. For subtraction, basically the same thing. You just make sure you do a minus c. You do b minus d as well. And again, if you had to subtract two vectors that you had their component forms for, you could easily do that and get the resultant vector to go along with that. In addition to that, you can multiply by a scalar value. What that means is that you would be multiplying your vector by some number, which ultimately just changes its magnitude. Okay, so if that value is k, what you would do is just distribute it to each of the components. So you get k times a, you get k times b. Okay, to be very clear here though, multiplication with a scalar value is not the same thing as multiplying two vectors. That is a completely different ballgame. In fact, there are two different ways to multiply vectors. We have the dot product and we also have the cross product. At least one of those we will take a look at later on in a separate set of notes. In example 3, we've got two vectors, u and v, and we have their component forms. What we're going to do is practice adding, subtracting, and even multiplying by scalar values when in component form. All right, so u plus v, really all you got to do here is take the horizontal components, the 1 and the 2, go ahead and add those together, which is going to give you a 3, and then you're going to take the y components, -3 and 5, and add those together, which is going to give you a 2. And that's it. That's all you got to do when you're adding vectors u and v, given the component form. Okay, it makes it much easier to get an answer out of that. All right, the subtraction, u minus v, okay, we're going to take 1 and we're going to subtract 2, which is going to give us -1. We're going to take -3 and subtract 5, which will give us -8. For the next, what we're going to do is double up u and triple up v before we subtract those two. Okay, so 2 times u is going to give us 2 and -6. It's going to give us 2 and -6. Okay, and then we'll be subtracting, let's see, tripling up v is going to give you 6 and 15. Okay, so now then subtracting, we'll need to distribute. You're going to have 2 minus 6, which will give you -4, and then we also have -6 minus 15, which will give you -21. Okay, go ahead and box that one since there's a little bit more to that problem. All right, and then for the last, we're going to multiply u by 4, which is going to give us a 4 and -12. For v, we're going to double that one. That'll give you 4 and 10. Okay, and then when we add them together, we're going to get an 8 and -2. And that's pretty much all there is to that.
Wait, there was.